All right, welcome back to Finite Element Method. This is class number 3, Math 574 here at the University of Tennessee, where we're learning about the basics of the finite element method. And before we really understand how finite element works, we're talking about something called the Galerkin method. And to do that, we proposed a model problem based on a Poisson problem. And so now we're talking about abstract versions of that. And we're talking about things like Say's lemma and so on and so forth. These are all the basic building blocks behind the finite element method. We haven't really gotten into the nuts and bolts of finite element method yet, but we're getting there. So today I want to talk about, we talked last time about something called Hilbert space and Banach space, and we talked about, um, we've already talked about norms, and we've talked about what it means to be convergent and what it means for a sequence to be Cauchy and all that stuff. So that gives us all the right framework to make an abstract setting for the problem that we have that's of interest to us. And that is kind of like, if you want to think about it, it's an abstract version of what's called the Poisson problem. So we need a new definition to really put this thing on a full abstract setting, and we need the definition of what's called a bounded linear functional. So here it is. So suppose that V is a Banach space, then the mapping F, which takes objects in the Banach space and maps them to the real numbers. So how does this work? Well, a Banach space could be a space of functions, remember. We've already, well, we'll get into better examples of this momentarily, but these points or objects here in the Banach space can be quite complicated. So I want you to think about this as not simple points, but as objects, okay? They can be things like functions or vectors. In any case, it's going to take those objects, those vectors, those functions, whatever they are, and it's going to map each one of those to a real number. This function is called linear, kind of obviously, if and only if it's what we mean usually by linear. F of alpha u plus beta v is equal to alpha f of u plus beta f of v. For all alpha and beta, those are what we call scalars for our Banach space. And by the way, all our Banach spaces and Hilbert spaces and all of our spaces that we'll consider are all going to be what we call real spaces, okay, or spaces over the field of real numbers. That means the scalars for those linear spaces are real. For all scalars, alpha and beta, and all vectors or objects from the Hilbert space, or well, in this case, it's a Banach space for all objects in the Banach space U and V. Okay, so this is what we usually mean by linear, right? So there's no content there which is new. Such a mapping is called bounded if and only if there is a number m greater than 0 such that the absolute value of f of v is less than or equal to that constant m times the norm of v for all v in v. All right, so this is exactly what we mean by bounded. By the way, this statement, the fact that it's linear and the fact that it's bounded, will also imply that these functions, that these objects are what we call continuous. And I'll have homework problems which take you through that. The set of all bounded linear mappings from V to R has a special designation, has a special notation. It's called V prime. Okay, so you've probably seen this if you've taken a course in higher analysis before, if you've talked about Banach spaces or Hilbert spaces, and it's called the dual space. So this is a common notation. If we have W as a space and we want to designate its dual space, we'll simply say W prime is its dual space. Okay. Now, those two objects are not the same. The stuff in here is, let's say, vectors, and here is the set of all bounded linear mappings of vectors into R, those vectors into R. Okay, so one is the usual Banach space and the other one is the dual space. Okay, so now remember we're heading in the direction of making some sort of abstract version of our model problem. So we have these things called functionals, and that serves as our kind of in the same role that F satisfied in our model problem, in our model Poisson problem. In that case, in that setting, F was what we called the forcing function or the force. Um, is that what I usually call it? Yeah, I think I usually call it the forcing function, something like this. In any case, this functional that we just defined is going to have the same role as the forcing function did in our model problem. We need another object which is going to play the role of the bilinear form A that we derived. So let's make a kind of obvious definition then. Suppose that V is a Hilbert space. I'm not sure why I switched from talking about a Banach space up here to a Hilbert space here. Doesn't really matter. I could have kept them both as made them both Hilbert spaces or both Banach spaces. It doesn't matter because, um, in fact, I didn't even have to make them complete linear spaces. I could have just used a normed linear space, for example. But okay. Ultimately, we're going to be using Hilbert spaces in most of these locations. So suppose that V is a Hilbert space, a mapping A, which has two inputs. The first input is from our Hilbert space V, and our second input is also from that Hilbert space V, and it maps those two vectors, those two objects, functions, whatever they are, into real numbers. And this mapping is called a bilinear form, if and only if, well, you can imagine what the definition is. It's got to be linear in both entries of A. To be bilinear, that means it's linear in the first and linear in the second entry. So what does it mean to be linear in the first entry? A of alpha U plus beta V against W is equal to alpha A U W plus beta A V W. In other words, it's simply exactly just linear in that first entry. And it has to be linear in the second entry as well. So A of U alpha V plus beta W has to be equal to alpha A U V. So we're talking about that one first. And then beta A U W. So the second entry. So this has to hold for all scalars, alpha and beta, and all objects that we're dealing with in the Hilbert space or Banach space, U, V, W. So this is what we mean by a bilinear form. It's linear in both entries. It's bilinear. Now we need some further abstraction. We need a little bit more information. We say that A is coercive if and only if there exists a constant alpha greater than 0 such that AVV is greater than alpha times the norm of V squared for all V and V. So again, I didn't have to, in fact, this doesn't have to be a Hilbert space. I'm going to change it on the fly. By the way, I didn't get the chance to upload these notes before class. They'll come right after the class. Let's make V a Banach space. We don't need it to be a Hilbert space yet. So for V to be a Banach space, it's a normed linear space that is complete. Well, to be a normed linear space, it has to have a norm associated to it. So the norm associated to it, there's some norm out there which is associated to it. This one is going to be the standard one. Whatever that space is, this is the standard one for that, the one that's usually identified with that space. So in or with respect to that norm topology, that norm, um, remember, so if I say something like the norm topology, does everyone know what I'm talking about? What I mean is the norm tells you how sequences converge. It tells you how to make open sets, and therefore it generates what's called a topology. So the norm is gives a topology on V, and there's some norm out there which is the standard one for the space. If I don't designate it otherwise, we're just going to say it's whatever it is for that space. And I'll always denote that as, or with this symbol, okay, subscript V. That's the standard norm on the space, whatever the heck it is. So this coercivity definition is measured with respect to this norm, whatever it is. So notice that all this stuff here is positive. It's a positive number, right? And as long as v is not equal to the zero vector, this object over here is going to be a positive object. So what it's saying is that if I put v in both locations, both entries of this bilinear form A, then that's greater than some positive number. So this object this stuff here has to be positive, right? Um, and it stays away from it. So this statement here is saying that it's staying well away from zero. That's kind of what coercivity means. Later on, we'll draw pictures of what this means sort of graphically. I don't want to belabor the point too much. Um, this is our definition for what we mean by coercive. So this is like the coercive is the lower bound part. So now I need what's called I need some sort of upper bound part. And that is where the concept of continuity comes in. We say that A is a continuous bilinear form if and only if there exists another constant, gamma, also positive, such that, and this one I don't have to put any I'm not putting the same entries, or I'm not putting the same object in both entries anymore. AUV is less than gamma, that's our positive constant here, times the norm of U times the norm of V. Again, these objects here, as long as U and V are not equal to the zero objects in that Banach space, all of these objects here are positive. This um, doesn't necessarily have a sign. It could be negative, right? It could be a negative number if I put in U, particular U and some particular V. But all I need to know is that this number, remember that's just a number because this bilinear form takes two objects and maps them to a number. This number has to be under this positive number. Okay, so that's what we mean by a bilinear coercive continuous form. So now we're ready to state our abstract problem. And by extension, we're able to define the abstract Galerkin method. All right, so what we want to do now is we're not going to, we had a model problem. It was we posed it initially as a strong form problem, so it was the PDE, and then we multiplied by test function, integrated by parts, right? And we came up with this so-called weak formulation. So our abstract problem is going to be an abstract weak problem. It's going to look like the weak formulation of the boundary value problem that we gave last time. Suppose that A is a continuous and coercive bilinear form, and F is a bounded linear functional. It's in the dual space of V in particular. Okay, so our problem is find U and V such that A u v is equal to f of v. So this is our bounded linear functional. Every time we put in an object from the Banach space, we're going to get a number here. And we're saying this real number equals this real number for every v that we want to pull out. These are called our test functions, every test function v in the Banach space. Okay, or Hilbert space. I guess here I'm still going to make this just for now a Banach space. Okay, so why am I making it a Banach space? Because it doesn't Hilbert space is extra structure that I just don't need yet. Now, what am I going to assume about VH? All that I need to assume about VH now to make my abstract Galerkin method run is I need VH to be a finite dimensional subspace of V. That's it. So the abstract Galerkin approximation of that abstract weak problem, so this is 3.1 is my abstract weak problem. The abstract Galerkin approximation is similarly and easily defined. Find UH in VH such that A of UH V is equal to f of V for all test functions V, but the test functions here for the abstract Galerkin problem are in VH. Okay? They're in VH. That's it. That's our weak, abstract weak problem and our abstract Galerkin approximation of it. Again, all that we're assuming about A is that it's a continuous course of bilinear form. F is an abstract object called a functional, right? So that's, actually, I didn't call it a functional, did I? So these functions F are called functionals. So you might wonder why F is called a functional instead of just a function or just a mapping. The reason why it's called a functional is because it's a function of functions in many cases. It's a function of functions. And so they wanted a different definition or a different name for such a structure. And so they called it a functional. That's my guess. That's my guess as to why it's called that. Any case, so F is this abstract object called a functional. And this is some abstract objects. I'm simply calling it a bilinear form. So notice this has absolutely no connection now possibly to a PDE. So initially, from the first day of classes, we started with what? What did we start with? We started with a partial differential equation called the Poisson equation. And we called it the Poisson problem when we coupled it with those boundary conditions. We multiplied by a test function and integrated by parts. And so that gave us a weak formulation that looked like this. Let me put my differential element in there. And we gave this a name. I think I called that capital F. And we gave this a name. I called that A of U and V. So this we called our symmetric bilinear form in that case. All right, so now we're generalizing this all the way to the point where there's no PD at all in sight. It's simply an abstract problem. So I hope you don't mind abstract problems. I mean, you're mathematicians, you're, I guess, mathematicians in training. Um, it should be par for the course that everything that you define in mathematical terms eventually somewhere gets abstracted. Now, we're not going to do abstraction for abstraction's sake in this course. We're going to be really interested in PDEs, but I'm going to deviate a little bit from the PDE track to give you this kind of abstract setting, because the abstract setting allows us to do a lot really fast. We don't have to repeat the same analysis over and over again just because the partial differential equation changes slightly. We can do this in this abstract setting, do it completely generally, and then the mathematics that we derive from that applies for a large swath of problems. That's why we're doing this in this abstract way. So we define this abstract problem. Now we have its abstract Galerkin approximation. What are the objects, or what are the characteristics of the abstract Galerkin approximation? It has exactly the same structure. It uses exactly the same bilinear form, exactly the same functional f, but notice that the test space changes from being every v in the Banach space to every v in the finite dimensional subspace of that Banach space called VH. Okay, so that's the key element of the abstract Galerkin approximation. Moreover, we're seeking the solution of the abstract Galerkin approximation in the subspace, whereas the solution of the original problem must be sought, for reasons which I'll get to momentarily, in the larger Banach space. Okay. Now, as I said, we don't need to abstract yet to Hilbert space just to define this problem. But at this point, it makes sense to do so when we start talking about this thing called the Lax-Milgram lemma, which is really a theorem, actually. Okay, so let's see how it goes. Let V be a Hilbert space. Suppose that A is a continuous and coercive, but not necessarily symmetric bilinear form on A, or on V. Let F of V prime be given. Then, right, this means a bounded linear functional in the dual space. Then there exists a unique solution to problem 3.1, our abstract weak formulation. There it is right there. So it's a little bit like magic. We're saying, as long as I assume the right things, this problem that I stated here magically has a unique solution U, which fits this 3.1. Now, what are the details of this? So I'm skipping some of the details because they're quite complicated. Some of you may have seen the Lax-Milgram lemma before in the setting of PDEs. Some of you may have seen it in other places. What are we assuming about A to get this? Well, we're assuming that A is a continuous and coercive bilinear form, but we're not necessarily assuming that A is symmetric. We are assuming that F is a bounded linear function from V into R. So that's what we call a functional. Then we know that there exists a solution to 3.1, kind of like by magic. But it's not magic, it's mathematics. We assumed all the right things for the solution to exist and to be unique. Now, I can't show you the existence part because that requires a lot of machinery. For that proof, you can see Brenner and Scott, which is one of the two references that I gave for this course. Brenner and Scott's kind of nice because it's for more or less self-contained, so it can give you a nice introduction to functional analysis, which is where this theorem lives in this topic called functional analysis. The existence is a little bit beyond me, or beyond this course, but the uniqueness is really easy. Suppose that U1 and U2 are solutions to 3.1, right? So what does it mean to be a solution to 3.1? So it means that U1 satisfies 3.1 for all test functions V and V, and U2 satisfies the same equation for all test functions V and V. So I can subtract those two instances and use the linearity in the first argument for A. And that's exactly where this line comes from. If I subtract those two equations, where I have the solution for U1 and U2, subtract the two, use the linearity of A in its first argument, I immediately get this statement. Now, what does this statement mean? You can't immediately conclude that U1 is equal to U2, but let's use our coercivity statement. So our coercivity statement says that, well, we're allowed to put anything in the second position that we want, but if we put the same object in the first location as in the second location, or the same object in the second location as in our first, then our coercivity statement says that has to be greater than this positive number alpha times this norm, right? Where it's the norm of whatever object we put in there. Well, norm squared, actually, when measured in the usual norm of V. Okay, so that norm squared is going to be of U1 minus U2. And of course, as I said before, normally this guy is going to be a positive number unless this object is equal to zero. Could that be equal to zero? Well, we know that this is equal to zero for every v that we put in there. If I put in v equals u1 minus u2, it's still true. So zero is equal to all that. Coercivity tells me that I have this inequality, and this inequality, right, involves this number. This number is going to be, this is positive. This is going to be positive, but only if u1 is not equal to u2. In other words, u1 minus u2 is not equal to zero. Now, it could be equal to zero, and in this case, it has to be equal to zero because we have zero is greater than or equal to zero. Well, that means that forces every object in this line of reasoning to be zero for these inequalities to be maintained um, in a standard way. Every object has to be equal to zero. This object in particular, this can't be equal to zero. So the only possibility is that this norm is equal to zero. But if that norm of that object is equal to zero, that means the object inside has to be equal to zero. But the only way that that can happen is if U1 is equal to U2. So that's the uniqueness proof. As I said, the existence proof is a lot more complicated and involved. So we'll skip that. So what do we know? We know that the abstract problem that we posed has a unique solution, no problem. Now, with the hypothesis of the last theorem, that is the Lax-Milgram lemma, the solution U is stable in the sense that the norm of U is less than m over alpha. Okay, stable in this sense. So this stability will make better, this will make a little bit more sense whenever we're looking at the abstract Galerkin approximation, as I'll show you in a moment. Okay, so how do we prove this, the statement 3.3? Well, the solution U of V to 3.1, remember we just said it's unique and it exists and is unique, so it has to satisfy that. There's one and only one thing that does that. Now, let's put U in as a test function. Are we allowed to do that? Yes, you're allowed to do that because U is in V and every test and the test functions are also in the space V. At this point, we're assuming that V is a Hilbert space because we need it to be Hilbert in order to use the Lax-Milgram lemma. Okay, so normally we would just be working in a Banach space. We wouldn't need the inner product. Now we're working in a Hilbert space. So put in U in for the test function because it's also in the Hilbert space. Well, we have the coercivity statement has to apply because we're putting in U for in both entries of that bilinear form. So this is greater than that object over there. Now this is equal to f of U because I put U in for the test function. So now I have f of U over here. That's less than or equal to its absolute value, of course. Now, this is less than m times U the norm of U in the regular norm on the space V, um, that's because of boundedness, right? So this one is the coercivity statement, and this one is because of the boundedness of the linear functional. Well, now I've got it because I've got norm of U on both sides, and I'm going to cancel one of them. As long as U is not equal to zero, then I can apply the cancellation property because if I know that U is not zero, then the norm is definitely not zero. I can divide by the norm of V and I get this statement immediately, which is exactly the statement I wanted to prove. Which doesn't, this doesn't make much sense as not so useful at this moment. It's going to be much more useful in the context of the Galerkin approximation, as I'm going to show you in a moment. Now, you might say, well, I haven't covered all cases because I said, suppose that U is not equal to zero. What if U is equal to zero? Is that possible? It is equal to zero. It is possible that U is equal to zero, but notice that in that case, this would be satisfied trivially because if U was equal to zero, this is just equal to zero, and zero is going to be less than this positive number, less than or equal to that positive number. So there's nothing really to show there. Okay, so we've just shown it. Now, I claim that I can do exactly all of the same calculations for the abstract Galerkin approximation as well. With all of the same hypothesis as in the last theorem, if VH is a finite dimensional subspace of V, then there is a unique solution, UH in VH, to the Galerkin approximation. And moreover, this solution is stable in this sense. Let's see, do I have a proof for this? No, no proof. So what is the proof for this? So this proof is going to be an exercise in the homework. But what are the details of the proof? Well, the details of the proof are this. I need to be able to apply the Lax-Milgram lemma to this same problem, but in the setting of VH. So the question is VH still going to be a Hilbert space? And the answer is yes. It's going to be a Hilbert space because it's a finite dimensional subspace of a Hilbert space. That's always going to be a Hilbert space. In fact, um, if it's a finite dimensional subspace and it's no matter what, it's always going to be a Hilbert space. Okay, so as soon as I can as soon as I can assume that it's finite dimensional, then I'm fine. The Lax-Milgram theorem is going to apply, and I'm going to be able to conclude for the finite dimensional subspace problem, that is the abstract Galerkin approximation, that I have a unique solution, and everything is going to be exactly the same as it was above. I can still basically I can repeat all of the same calculations, but instead of doing the calculations for U in V, I'm doing them for UH and VH. Okay, but all of the same calculations apply. There's nothing really different I have to do. But the analog of this for the abstract Galerkin approximation means more than it does in this setting. Okay. Okay, so that is now becoming a very important statement. It really does mean that this is stable. Okay, so this stability, or let's call it a stability statement. So why do we call this stability? Well, this is completely independent of the finite dimensional subspace that I choose. And we're going to see that in when we're doing the finite element approximations, we can choose lots of different finite dimensional subspaces. In fact, they're going to be parameterized by this parameter we're going to call H, which is going to be the mesh spacing. You don't have to worry about any of that right now. But I'm going to be able to choose this finite dimensional subspace in a lot of different ways. And in fact, I can choose it in such a way, and usually this is the idea of what's called mesh refinement. If I make h smaller and smaller, then the dimension of this space becomes larger and larger. So in other words, it's kind of like as h is growing, this guy is kind of getting bigger. As h gets smaller, VH gets bigger. It grows. Okay, so I can think about it like this. As h gets smaller, this VH kind of starts, its dimension starts blowing up. Basically, this VH starts to converge in some sort of weird abstract way. It sort of converges to V. It's V we can think about as an infinite dimensional object, whatever the heck that means. So if you've taken functional analysis or applied linear analysis, we talked about this concepts, at least whenever I taught it, and your instructor likely did as well, talked about these objects called infinite dimensional spaces. Well, what's going to happen in this setting is VH is always going to be finite dimensions, but its dimension can get larger and larger and larger and larger until it kind of fills up this space in the limit as h goes to 0. In that sense, VH kind of becomes infinite dimensional. Um, so why is this important then? Why is this estimate here important? Well, because what it says is that as my dimension, or as the dimension of my space gets larger and larger, okay, this object is still kind of bounded by this rock solid object up here. This never gets bigger because this M is only the M which is defined by the F, okay? And this alpha is the coercivity constant only defined by the bilinear form A. These two objects never get bigger. They're independent of the dimension that I choose. But this guy kind of gets pinned above by that. It says that in some sense this is stable because it never gets bigger than that. Okay? So that's why this is really a statement of stability, and it means a whole lot more in this abstract Galerkin, or for this abstract Galerkin approximation, than it meant up here for this solution V, because in this sense, we usually imagine that V remains unchanged. Okay. And only the VH gets bigger and bigger. Okay.
Quick question.
Yeah.
So the M and the alpha for 3.4, is that going to be the same or have some sort of connection to the M and the alpha in 3.3 for the infinite dimensional space, V?
Great question. Yeah. They're exactly the same. Okay. Because remember, F and A are kind of like the data. They kind of define the problem. Okay. The other thing I want to mention is, so yes, the answer to your question, M is set by F and alpha is set by the A bilinear form. They are the same in 3.3 as they are in 3.4. Excellent question. Here's another good question, or another important point, I should say. Nobody asked the question, but it's a good point. So notice that this is the V norm here. It's the same norm here. Okay. So that's usually quite important because V, we have two spaces floating around, right? We have the space V, and that's remember it's a Hilbert space, so it's got a bilinear form or an inner product associated to it, which gives rise to a norm, right? So the question is, what norm and bilinear form do we use for the finite dimensional subspace? The answer is we use the exact same ones. That's a very important point. I'm using for those guys, let me just do it this way. Copy and paste. So whenever I look at this space VH, which is the finite dimensional counterpart, even though I'm looking at a finite dimensional version of V, the inner product and the norm that I use are still crucially exactly the same. Okay, so there are a lot of hidden things that stay the same whenever I look at the weak form versus the abstract Galerkin approximation of it. And some things, the only really, and this is important, the only thing that changes is VH. Okay, VH becomes a finite dimensional subspace of V. Any other questions? All right, so now that we know that our weak formulation has a unique solution, and our Galerkin approximation in the abstract setting has has a solution. We can talk about measuring the error between the true solution and its Galerkin approximation. So again, we're going to be in the case where we're not assuming that the bilinear form A is symmetric yet. So this is the non-symmetric version of Say's lemma in the abstract framework. Suppose that A is a coercive continuous bilinear form on this space V. We can assume that B in this setting is now a Hilbert space because we really need the solution to exist and be unique. Suppose that F is in V prime, that F is in the dual space, so it's a bounded linear functional. Let VH be a finite dimensional subspace of the space V, which is a Hilbert space. Okay, so now, of course, we have all the framework, the setting for Lax-Milgram lemma to apply. Let U in V and UH in VH be the unique solutions of 3.1 and 3.2 respectively. Then AU minus UH against the test function V is equal to 0. So this is like the fundamental Galerkin orthogonality that we had before. Fundamental Galerkin orthogonality. Except that it's no longer an orthogonality because this A is not going to be an inner product anymore. And the reason that's case is A is not even a symmetric object, so it can't be an inner product. All inner products are symmetric. But it's like the fundamental Galerkin orthogonality, and it's just as important as it. Furthermore, the norm of U minus UH measured in this norm V is less than gamma over alpha times the minimum of U minus V taken over V and VH. So I'm leaving this as a homework exercise. The proof of it is quite a lot like Say's lemma originally, except now I have to use, I'm going to try to guide you through this in the homework. You have to use the coercivity, the continuity, and um, so let's see, how can I put it? You have to do things slightly differently than we did them for the model problem. Let me just put it that way. But the homework should guide you through that. So I'll leave that as homework exercise.
Dr. Wise, you had
Yeah.
a slight typo in your writing. You wrote UNVH, not UHNVH in the statement of the lemma. The you have let U in V and U in VH.
Oh, yeah. Okay. Okay. Thank you, Daniel. All right. Um, everything okay now?
Yes, I think so.
Okay. All right. So that's the abstract version of Say's lemma, which I'm going to ask you to prove in homework. Now we're going to go through we'll go through the symmetric version of that. And to do the symmetric version of the problem, we need something called the Riesz representation theorem. Um, I guess this is a little bit out of place. So let me take this and put this up here. Through the magic of, there we go. So now I want to talk about the symmetric problem, and to do the symmetric problem, we're going to use Riesz representation theorem. How many of you have heard of this? Show me a show of hands. How many of you have heard of Riesz representation? Okay, so some of you have heard about Lax-Milgram, some of you Riesz representation. So probably more of you have heard about the Riesz representation theorem for various reasons, but it's going to be it's like the analog of the Lax-Milgram theorem, except that in this case we can assume that well, in this case we'll be assuming that A is a symmetric bilinear form. Okay, so but I'll get on to that in a second. So let V be a Hilbert space with this particular kind of inner product we're going to call the star inner product. Now this might be different than the usual inner product on the space V. And we're going to let F, as usual, be a bounded linear functional. Then there exists a unique U. This is called the representation of F. There exists a unique U in V such that F of V is equal to U against this test function V for all V in the space. So in other words, if I have a bounded linear functional in the space, that can be mimicked or exactly described by some particular function which is called the representer of F, and the action of F can be described through the action of the inner product of V against that particular representer. So in other words, F is like an inner product, or can be modeled like an inner product. So now the important thing here is that this holds for any inner product that I want to use on the space, as long as the space is still a Hilbert space with respect to that inner product. Um, and so the proof for this is a bit beyond what I want to do in this course, and it can be found in Brenner and Scott. But we're going to use this instead of using that harder, more complicated object called the Lax-Milgram theorem whenever we have A as a symmetric bilinear form. So suppose that F is another given bounded linear functional, and A is a symmetric, coercive, and continuous bilinear form on V. Now we're going to consider the symmetric version of the abstract problem, right? So the symmetric is exactly the same. And in fact, I even thought about just making it the same, leaving it the same numbers, but I thought this might just be easier for reference sake. So in structure, our symmetric problem is exactly the same as our original problem, which I think I called 3.1. And our symmetric Galerkin approximation is the same as the abstract Galerkin approximation. The only difference here is that underlying all of this, A is a symmetric bilinear form. All right. A is still going to be coercive and continuous. We're going to add this extra little layer to everything, and we're going to say that A is a symmetric, coercive, and continuous bilinear form. So it gives us a little bit something extra. Okay, so here's the proposition that I want to state, and its proof is kind of easy. So if A is a symmetric, coercive, and continuous bilinear form on the Hilbert space V, then A is a bona fide inner product on V. Okay, and this is probably going to be different than the inner product that's already on V. And so we're going to give, and this inner product has a different structure and a different name. We're going to call it the A inner product. The usual inner product on the space is usually given this symbol. Okay. Now, A, because it's an inner product, is going to give rise to a norm. and that's what we call the energy norm. So this object here is a bona fide norm on V, and it's equivalent to the base norm on V. In other words, what the word equivalent in terms of norms means something very important. It means there exists a constant C1 and C2 such that C1 norm V in the energy norm is less than norm V in the base norm, which is less than or equal to C2 times the norm of V in the energy norm for all V and V. So that means that the topologies that these things describe are exactly the same. So if you have a convergent sequence in one of these topologies, then you have a convergent sequence in the other. And if you have an open set in one topology, then you have an open set in the other. They give equivalent topologies. Okay. And really that's what I mean by topologies. It means convergences mean the same, and open sets are the same. Okay. So V paired with this new inner product A and VH paired with this new inner product A are Hilbert spaces. Of course, the latter being finite dimensional, and these Hilbert spaces are topologically equivalent to the original spaces. Okay, so the spaces are the same, but the way you create open sets may be different. But it turns out, since I'm saying they're topologically the same, the way of creating open sets is exactly the same. Okay, sequences, if I say that a sequence converges in one topology, then it converges in the other. By the way, what kind of topological differences are there between, so what does it mean when I say an inner product space has a topology? Well, an inner product gives us a norm, but it also tells us, it gives us kind of angles between vectors, right? That's what an inner product does. And the kind of canonical example of this is the dot product, right? Um, and so knowing angles between vectors doesn't change how things converge. It just gives us a little bit more information. Okay. The important thing, I guess, from the topological standpoint is how I create norms and what those norms ultimately tell us about open sets and convergences. Okay, so if this is all true, and by the way, this turns out to be not that hard to prove, because of what? Well, the proof of this is really an easy exercise. Oops, that doesn't make any sense. So what's the proof? Well, the proof is I have to show that this is an inner product. Yeah? If I can show that this is an inner product, then this is going to be a norm, no problem. How do I arrive at that? Well, I need to show, well, let's answer the first question first. How do I show that this is an inner product? Well, it's going to involve the coercivity and continuity of that bilinear form A. But I need one extra thing to get a norm or an inner product, and that's just the symmetry. In fact, if I have those three things, then I'm always going to have an inner product. If you have a symmetric, coercive, continuous bilinear form, it's really pretty easy to show that you have an inner product. And this is involved in, is basically wrapped up in the same ideas. Once I have an inner product and I know that I have coercivity and continuity with respect to the base norm, then I have to produce an induced norm from that inner product, which is equivalent to the base norm. It's all, these things actually follow pretty quickly. Once I know this information, then showing this point 3 actually becomes fairly simple as well. So I have some homework problems that address this, and you'll see these questions are not that difficult to answer. Okay, so now I know that A, the symmetric coercive continuous bilinear form is exactly is precisely an inner product, and it gives me an equivalent inner product to the one that I started with. This doesn't always have to be true. I mean, I could create an inner product which derives a topology or produces a topology which is different than the one that I have for my norm. And so it in one case I might produce a Hilbert space, and in another case I might not produce a Hilbert space. Okay, but in this case I do. It produces the same. I you know I have equivalences. Okay, so if A is a symmetric coercive continuous bilinear form on the Hilbert space, and if F is a bounded linear functional, then the problems 3.7 and 3.6 and 3.7 are uniquely solvable. In fact, I don't have to appeal to the Lax-Milgrom theorem to show this. I can show a much easier proof using the Riesz representation theorem. In fact, I already knew that this was solvable because all I'm doing is adding another feature. I'm adding symmetry. It's just that the proof is a lot simpler. This follows from the Riesz representation theorem since these two objects are now Hilbert spaces. And the fact that they're Hilbert spaces means that these are inner products, right? Which give me a topology which is complete. So I can apply Riesz representation, and that says that there's a unique representer, right? There's a unique representer U such that for every F, F of V is equal to A U V. So this becomes the representer of F, but in this inner product, okay? And likewise, for every, or sorry, there exists a unique UH in VH such that F of V is equal to AUH V for all V in VH. Okay, so this becomes the representer of F in this inner product. Okay, and the Riesz representation quickly gives me this existence and uniqueness that I need. Of course, I already knew that I had existence and uniqueness because all I'm doing is adding something new to what I already knew um, from my previous situation. It's just that the proof is a lot simpler. Okay, now I have a symmetric version of Say's lemma. Again, I'm not proving this because the proof is quite a lot similar to what we've done before, and you're going to revisit this in homework. So with the same hypothesis as in the last proposition, I have a couple of facts. The first one is the fundamental Galerkin orthogonality and best approximation. So this really is like the Say's lemma that we proved a class or two ago, because the very first model problem I gave you had a symmetric coercive continuous bilinear form. Okay, and so this case is just the abstracted version of that. So the details here are fairly similar. This is my fundamental Galerkin orthogonality. Furthermore, what else can I say? With the same hypothesis as above, I can also recast the weak formulation as an optimization or variational problem. With the same hypothesis as in the last proposition, let's define this object, which I'm calling G. G of V is equal to 1/2 A VV minus F of V. So if you remember back to the model problem, this is exactly going to be the same as that was, the model PDE. Okay, so this is what I call an energy, and I'm going to minimize that energy. Then the following problems. So this is an optimization problem or a minimization, and this here is what we called previously the Ritz-Galerkin approximation of that. These problems are equivalent to problems 3.6 and 3.7. Those are the symmetric weak approximate or weak problem and the symmetric Galerkin approximation. So those two problems we saw have unique solutions using our Riesz representation theorem. What I'm saying with this proposition is that now these minimization problems, where in one case I'm minimizing over the space V, and in the other case I'm only minimizing over the finite dimensional subspace of V called VH. Okay, I'm setting U equal to the first argument that minimizes this and UH equal to the argument that minimizes this over VH. These two problems, these are minimization problems, are equivalent to 3.6 and 3.7. They're equivalent to 3.6 and 3.7 respectively. So now, if that's true, if we know that they're equivalent and the proof is radically similar to the proofs we gave for the model PDE problem, um, if we know that the proof, or if we know that the solution sets are the same, and we know furthermore that these have unique solutions, then that means that these two problems here and here also have unique solutions. Okay, or in other words, are uniquely solvable. So I'm calling this a fun exercise, even though I would say it's probably um, not all that fun, but it is at least exactly the same as the proof that we gave previously for the model PDE problem, the model Poisson problem. Right. Okay. So this is all of my abstract uh, Galerkin approximations in the symmetric and in the non-symmetric case. So that takes care of all that. And as I said, there'll be some homework problems which address those. So hopefully, um, this may seem like abstract nonsense to you. It may be all perfectly sensible to you. I don't know, but I do believe that the homework will help to draw this in and make this a little bit more clear. The next topic that we need to talk about, and we won't get very far with today's lecture, is something called weak derivatives. To tell you what weak derivatives are, I could just do everything in one-dimensional space. I've chosen instead to do things in the d-dimensional setting, just because I I don't think it's that much more complicated to do this in the multidimensional case. So I need to tell you what is called a multi-index. So a multi-index of dimension d is a d-tuple, alpha equals alpha 1 up to alpha d. So I could put a vector symbol on top of this, and sometimes I used to do that. I don't want to do that because it's not a typical vector in the usual sense. So I'm just going to leave that off. So it's a multi-index. What does a multi-index mean? It means it's a particular type of d-tuple, one where all of the entries of that d-tuple have the following form. They're numbers which are non-negative integers. So that is to say counting numbers plus 0. So it could be 0, 1, it could be 2, etc. So it's the counting numbers plus I'm adding in 0. Um, so usually the counting numbers, and that simply means 1, 2, 3. And so my notation for the counting numbers plus 0 is just n sub 0. So we write, I'll sometimes write it like this. A multi-index will be written as something from this space, and this is the space of multi-indices. D-tuples, where the entries of the D-tuple of the tuple are from these from this set. The quantity where I take that multi-index and I put brackets around it. Basically, this looks like an absolute value, right? This quantity here means that you take the entries of that multi-index and you just sum them up. That gives you a non-negative integer when I sum those up because I'm summing non-negative integers. And this is called the order of alpha. Okay, so some of you have probably seen multi-indices before, maybe not all, but they're useful when you talk about PDEs. They're also useful if you talk about polynomials. So let me give you a quick example. Suppose that x is a vector in Rd. then we're going to use the following notation. If I take the vector x and I raise it to the tuple or the multi-index power alpha, this is not really raising x to the power alpha. What this means is this is notation, and what it means is um, take every entry of this vector x and we're going to raise it to the corresponding entry of that multi-index. And then we're going to take the product of that. So x to the alpha means we're going to take x1 to the alpha 1 power times x2 to the alpha 2 power times x3 to the alpha 3 power. This is useful for expressing things like polynomials. Okay, so and we'll come back to this example next time. So how can I quickly express a polynomial of degree, say, n or less, where it's a polynomial from Rd to R? Okay, so this is useful whenever I'm talking about polynomials from the space Rd into R. Okay, so then we can quickly write this polynomial in the following way. And this is going to look like a usual polynomial. So what's different about this from usual polynomials is the domain here is not R, it's Rd. Okay, so this polynomial can be expressed in a very quick way. It's a sum taken over all multi-indices with order less than or equal to n. And I want to remove that arrow there. Okay, that's how you read this. The sum over all multi-indices of order less than or equal to n of coefficients a, and need to remove that guy, times x to the alpha. All right, so we're going to come back to this example next time, and I'm going to explain to you why this is such a useful notation for expressing polynomials. You can look through this example that I give, the next couple examples that I give here, but we'll start here next time, and I'll end the lecture there.